in the last class, we have discussed about Coulomb's law and Gauss law and compared, and using Gauss law, we have derived Coulomb's law. And now, even this was discussed that Gauss law and Coulomb's law, although expressed in different forms, but are equivalent ways of describing the relation between the electric charge and electric field. In a static situation, these two laws cannot be applied in dynamic situation when charge is in motion. So remember, so these two laws can be applied in this situation. So Gauss law is more general and more fundamental. That was discussed in last class in comparison to Coulomb's law. Using Gauss law to determine electric field. This was also discussed in the last class. Gauss law is valid for any distribution of charges and for any closed surface. However, we can only calculate the field for several highly symmetrical distributions. So this is the steps for applying Gauss law to calculate electric field. This was discussed, and we came to this and plotted the graph like this. And now this question was also discussed, and this question was discussed in the last class. Now, question is that a uniform spherical cell of charge of radius r and surrounds the point. This was also discussed in the last class. And this is the case. A non-conducting spherical cell of radius r is uniformly charged with total charge q on it. Now we put point charges q1 and q2 inside and outside the spherical cell respectively. Look at here, one of the charge is placed at the non-conducting spherical cell. Q is kept here. And another 2-point charge, Q1 and Q2 is placed. Q1 is placed at the center of a spherical cell, and Q2 is at a distance of R2 from the center of a spherical cell, and Q1 is placed at a distance of R1 from the center of a spherical cell. Remember, capital Q is put over the surface of the non-conducting spherical cell here. So determine electric force on the point charge. So here, in order to determine force, first of all, we can determine electric field outside and inside, wherever it is demanded. So here in this case, inside the sphere, we have to find out first electric field, where charge Q1 is placed. And you know that charge Q1 is at a distance of R1 from the center of a sphere. So electric field due to the charge on the cell is 0 inside the cell because no charge is enclosed inside the cell. So remember here, we put a point charge Q1 and Q2 inside and outside the spherical cell respectively. Determine the electric force on the point charge. Remember here, will this point charge Q1 experience electrical force? Try to understand, no gossiping. Will this charge Q1 experience any force when placed inside the cell? What would be answer? Of course, answer will be 0. Why? Because you know that inside the cell, electric field is 0, and wherever electric field is 0, force experienced by the point charge Q1 will be 0. Because force equal to Q1 into E1. So inside the cell, electric field is 0. Therefore, force acting on charge Q1 is 0. Okay, so try to understand. I told you that no gossip, so, but you keep on gossiping. So, okay, okay. And now, okay. Now try to understand. Electric force expressed by the charge Q1 and when it is placed inside the dielectric or non-conducting spherical cell is 0 because inside the cell is electric field is 0, therefore no force will experienced by the charge Q1. Now come to the another point charge Q2, which is outside this cell at a distance R2 from this cell. So this at this point, at a distance of R from the center of the cell, there will be non-zero electric field E2. An expression for this electric field will be expressed as Q upon 4 pi epsilon naught R2 square. That is R2 square. Therefore, force experienced by the charge Q2 equal to electric field at this point into charge Q2. Okay, so the charge outside the spherical cell will experience electrical force. So now next thing is two cell law. If there is two cell, then we have to analyze here. Find electric field outside and inside the solid non-conducting sphere of the radius r. There is a solid non-conducting sphere. In the previous case, hollow or non-conducting spherical cell. So whether it is conducting a spherical cell or non-conducting spherical cell, electric field inside the cell will be 0. And even in case of conducting solid sphere, electric field inside the sphere will be 0. But in case of non-conducting solid sphere, electric field inside the sphere will be non-zero. So here is question that you have to practice. Find the electric field outside and inside a solid non-conducting sphere of radius r that contains a total amount of charge q uniformly distributed throughout its volume. In this case, in case of conducting solid sphere, whatever charge you give onto the surface of conductor, it will distributed over the surface only. But inside the solid sphere, conducting solid sphere, electric charge will be 0. But in case of non-conducting solid sphere, when you give the charge q over it, this will be distributed throughout the volume of this non-conducting charge sphere. Okay, so in this case, first thing we have to find out electric field at a point outside the sphere and at a point inside the sphere and at a point on the sphere. So first of all, just we have told you that first of all we draw the diagram for the charge distribution and then mark the direction of electric field line due to this charge distribution. And after that, third step is draw a symmetrical Gaussian surface that encloses the charge body. Here charge body is a non-conducting solid charge sphere. So it must be enclosed by another concentric sphere that will enclose it symmetrically. So this is the Gaussian surface. That surface must pass through the point where electric field is to be determined. So say if a small r is the distance from the center of solid sphere, and small r is greater than capital R, that is the radius of a sphere itself. And then in this case, the point will be outside the sphere because small r is greater than capital R. So now in this case, we find out electric field at a point outside the sphere. So for that one, first of all, we have to draw a electric flux through the Gaussian surface. So if you take elementary surface area dA or this Gaussian surface, then flux linked through this surface area is E dot dA. And therefore total flux through this entire Gaussian surface is obtained by integrating this E dot dA and giving this integral sign. And as it is symmetrically, so therefore distance from this center to all point on this surface will be same, that is R. Therefore, electric field remain constant. And only area is to be integrated. When area is, dA is to be integrated, dA becomes A equal to 4 pi r square. So E into 4 pi r square. This is the electric flux. Now from Gauss law, total electric flux enclosed through a surface is just equal to total amount of charge enclosed by the surface divided by epsilon naught. So we equate this electric flux with this. So total charge enclosed by this surface, this Gaussian surface enclosed total amount of charge Q, because total charge given onto the sphere is capital Q. Therefore, we write instead of summation Qi in A equal to capital Q. And we find electric field at the point outside the sphere. So outside the sphere, electric field will be capital Q upon 4 pi epsilon naught r square. So say this is equation 1. In this case, we see that electric field is inversely proportional to a square of distance. And this was the case for outside. Now we have to recall about the case for inside. So in case of you find the electric field inside the sphere, this is the outside the sphere. You don't need to do all the things here because it is completed only on this. Put here capital Q and then E equal to capital Q divided by 4 pi r square. That's enough. You don't need to move on this step. But still, let me describe these steps. How much charge is enclosed by this sphere? So you see, if volumetric charge density on this sphere is rho, and volume of this sphere will be 4 upon 3 pi r cube. So total charge contained on this sphere equal to volume of this sphere into volumetric charge density. So here, this is, and this is nothing but equal to capital Q. And this is equal to capital Q. Putting this value here, you see that electric field equal to rho r cube upon 3 epsilon naught r square. So C, rho is constant because charge is distributed uniformly. Epsilon naught is constant, 3 is constant, r is constant. So electric field is inversely proportional to a square of distance. If you go through this formula, but if you stay here only, putting total charge enclosed by Gaussian surface is capital Q because this solid non-conducting sphere contains total charge capital Q. So just put total enclosed charge equal to capital Q upon epsilon naught equal to E into 4 pi r square. Therefore, E equal to capital Q upon 4 pi epsilon naught r square. So capital Q is constant, 4 pi is constant, epsilon naught is constant. Therefore, electric field is inversely proportional to a square of distance. And this is the case outside the non-conducting sphere. Therefore, electric field is inversely proportional to 1 by r square outside the sphere. Now we come to the point inside the sphere. As soon as you move inside the sphere, a small r becomes smaller than capital R. Because now you move into the inside the non-conducting solid sphere. Then we have to calculate how much charge is enclosed by the Gaussian surface when we move inside the sphere. So say in this case, R is smaller than capital R when you are inside. Or one more thing, when you are onto the surface, then electric field will be just equal to, in that case, R becomes equal to R. So just put here capital R square. So capital R square get cancelled. So we get electric field rho upon 3 epsilon naught into R. So again here R is constant, rho is constant, 3 epsilon naught is constant. So electric field at the surface of a sphere is constant and maximum. Or even you can place here electric field equal to Q upon 4 pi epsilon naught R square, small r square. Or when you come to the point on the surface of the sphere, then small r becomes equal to capital R. So just you put here capital Q upon 4 pi epsilon naught capital R square. So electric field is constant and maximum at the surface of a sphere here. So 3 points is there where electric field we have to find. So first outside we have already found, and then onto the surface of the sphere. We no need extra effort to find out that. Just put a small r equal to capital R, then we find electric field on the surface of the sphere. Now we have to calculate electric field inside the sphere at a point which is at a distance of r from the center of a sphere, and small r is smaller than capital R. So in this case, electric field will be like this. Now remember how it happens. So we have to discuss about it. This result came in this way. When you are inside, then electric field becomes directly proportional to a small r. Therefore, when graph is plotted, graph will be a straight line inside from center of the sphere to the surface of a sphere. Now, question is that how it happens so. Problem is that just you have to draw a Gaussian surface. Let us say here is not given a figure of Gaussian surface. Inside, you just have to draw a Gaussian surface here. Inside, with radius r. Here, dot line. And then look over how much charge is enclosed by this Gaussian sphere. So similarly, same you have to apply the formula. Volume of this is Gaussian sphere into charge density rho. So charge enclosed by this Gaussian sphere equal to Q prime. Q prime equal to 4 pi epsilon naught small r cube into rho. So we find out rho and put here. And rho will be equal to what? Volume charge density equal to what? Total charge divided by volume of this bigger sphere. This is equal to rho. So total charge is Q divided by total volume of this sphere, that is 4 by 3 pi r cube. So therefore 3Q divided by 4 pi r cube. This is the volumetric charge density. Now, if you put the volumetric charge density here, you will see, or you will see that electric field is directly proportional to R. So now plot the graph in this way, and as distance increases from the center of the non-conducting charge sphere, electric field increases directly proportional to distance up to the surface of the sphere. And after that, if you move outwards of the sphere, away from the surface of the sphere, now electric field becomes inversely proportional to a square of distance. So graph will be like this. Okay. Next, this is also a question below. So for a sphere, each of charge Q uniformly distributed throughout its volume. चार स्फीयर है और सब पर चार्ज सेम दिया गया है Q. फर्क कितना है? सभी का साइज अलग अलग है. Rank the sphere according to their volume. सबसे स्मॉलर ये है, इंक्रीजिंग ऑर्डर में लिखा गया है, उसके वॉल्यूम के इंक्रीजिंग ऑर्डर में. So rank the sphere according to their volume charge density. तो अब इसमें हमें रैंकिंग करना है कि which sphere will have higher charge density, volumetric charge density. It is so easy. Just you have to know about how much charge contained on each sphere. So it is clear there in question that charge content on each sphere is capital Q. Now, in order to find out volumetric charge density, we have to divide the amount of charge contained on the sphere by its volume. So volume of which sphere is smaller? This is the sphere in A. So first sphere will have higher charge density, and second sphere will have a little bit smaller, and third one will have smaller than second one, and fourth one will have a smaller charge density in comparison to all. So try to understand. If you arrange in sequence, higher charge density will have the sphere, a smaller sphere, and then second one, and then third one, and last fourth one. Why? Because charge density is equal to charge per unit volume, because same amount of charge is there on every sphere. Only difference is that volume of each sphere is different. So those spheres which have a smaller volume will have higher charge density. So this one is the questions. So rank the sphere according to the magnitude of electric field. First case was the rank the sphere according to their volume charge density. Greatest must be kept first. The figure also shows a point P for each sphere, all at the same distance. So from the center of a sphere. Then rank the sphere according to the magnitude of electric field they produce at point P. Again, you have to remember here. As this point P is outside this sphere, so electric field due to this sphere at this point will be inversely proportional to a square of distance. And this sphere is onto the sphere. Therefore, here electric field will be inversely proportional to a square of radius of this sphere. And when we come to this point, because all these points are equidistant from the center of a sphere. So again here, first of all, we have to look into a sphere is conducting or non-conducting throughout its volume. So it is obviously it is non-conducting. So here electric field at this point will be directly proportional to R. Inside the sphere, electric field will be directly proportional to R. So in this case, R, in this case, small r, and in this case, small r, in this case, small r. All the cases, small r equal. Then electric field will depend on what? So remember here, in the previous question, it is correlated to here. Try to understand. Electric field is directly proportional to charge density, and electric field is directly proportional to cube of radius of a sphere, as well as electric field is inversely proportional to a square of distance. So in this case, you will see that charge density will decreases. R remains constant, and this R is same for all. So charge density in case of bigger sphere will be smaller. So electric field will be smaller or lesser. So those which have higher charge density will have high electric field. So just I have discussed there here. In this case, this sphere will have higher charge density because of low radius. So at the same distance, electric field will be directly proportional to volumetric charge density at this point, because distance small r is kept constant, and as well as directly proportional to radius of this sphere. So radius is constant, so we say charge density will be higher in all this case. Next, if you come to this point onto the sphere, so in this case, electric field will be directly proportional to charge density. So in this case, charge density will be a little bit smaller than in this case, or in this case, even smaller than this case, and even smaller in this case. So you have to conclude the result. Once again, you have to calculate, rank the sphere according to magnitude of their electric field they produce at point. I have discussed a lot about that one. So after discussing, your answer will be, first one is A, B, and then C to D. And after that, next question is, a uniformly charged non-conducting sphere has volume charge density rho. This has volume charge density rho. Now, material is removed from the sphere, leaving the sphere cavity. Now, try to understand a bigger sphere of radius R, capital R, say capital R. Now, out of this bigger sphere, a small sphere of radius small r is removed from this bigger sphere. So there becomes a cavity in the bigger sphere. Now, material is removed from the sphere, leaving the spherical cavity, so that their electric field through the cavity is uniform and is given by. So that the electric field throughout the cavity is uniform and is given by, where E is the where A is the distance of the center of the two sphere. Remember, here this is the center of bigger sphere, and this A is the distance between two centers, center of a small sphere and center of bigger sphere. This is the distance A. So even you can say that this A plus radius R2 and equal to distance from this center to this point here. Now we have to remember a proof. Replace the sphere with cavity with two uniform spheres. In order to solve this question, just we have to do, we have to look over the two spheres as a separate identity. And then first deal with the bigger sphere and then deal with the smaller sphere. And only difference is that the material that was removed from the bigger sphere, the density associated with the smaller sphere can be taken as negative. And every steps will remain same, only density can be taken as negative. And after that, we have to add up the electric field at a point due to these two spheres, applying superposition principle. So electric field, say electric field at a point R1 from the distance from the center, at a distance from the center of bigger sphere is E1, given by rho divided by 3 epsilon naught R1. Similarly, electric field E2 due to a smaller sphere is given by minus rho, because this material is removed from the bigger sphere, therefore it is taken to be minus, negative. So E2 equal to minus rho 3 epsilon naught R2. So after that, you just apply superposition principle. So after that, perhaps what's time? Is there?